So now that we have a solid understanding of equilibrium in 2D and forces in springs, we can actually move to a little bit more complicated structures, and complicated is not really that complicated if we build it step by step. But let's look at this system here. We have a more complicated structure in quotation marks, which has two weights hanging here and has the geometric configuration that is shown here. So let's read the problem statement and let's find out that we need to determine the tension in all cables if container F has a weight of 4 pounds and theta is 15 degrees. So let's put the information in here first. So this here would be 4 pounds and theta is equal to 15 degrees. And that is not a mistake. You may think like, how am I supposed to solve this? I'm short of one information here. And I would encourage you to pause the video right now and really try to solve this problem before I go ahead and show you how to do it. Because once I show you, you can never unsee it and you can never go through that learning experience ever again. This often seems like a problem that has not enough information for students because, again, the weight here for E is not given, but that is not a mistake, that is on design. So please try to work your way through it. And by working through it, I really mean work your way from node to node. So note that you have here AB, BC, and CD. And some of these nodes, with the information given, you can actually solve, whereas others you can. And I give you time to pause the video now before I move on. All right, I'm pretty sure you were able to solve it because you're fantastic mechanics students, right? So now I can explain to you how I would have done it. Let's take a look at the individual nodes. And let's remember that if I release a node, I can always release every node from its system. So I have one here, I have another node here, and I have another node here, and I have another node here. So first of all, let's kind of forget about A and D, because if I solve any one of these, I already know what's going on in the rest. But just so you understand how A and D is working, please understand that there must be a force that is pulling up, and because you have a force that is not vertical here, right? So this AB member is not vertical, it's not acting in this direction. It is actually pulling to the left. Therefore, the support here on the top actually has to react to it. And we will talk much more about this in the future, but you have to pull in that direction. Likewise, on the other side, you have to pull up and to the left. But let's forget those two now. Now, I probably intuitively would cut either node B or node C, and that's probably what you did when you solved the problem yourself. But let's understand why it is only possible to solve node B first. You could write down the equations for node C and you can draw the free body diagram and you will find that you cannot solve it. But why is that? That is because you have 1, 2, 3 unknown. And remember that we only looking at a 2D structure here. So we have the sum of the forces in X being equal to 0 and the sum of the forces in Y being equal to 0. So therefore you can only have 2 unknowns, right? 2 unknowns. And that is violated here in cut C or node C. Whereas in node B, you actually only would have unknown 1 and unknown 2, and unknown 3 is actually known because you know that there's 4 pounds pulling on it. So what you will do is you will first set up the equation for this node, and I will do that for you in a second, and then you take the information from here over to here so that effectively this one unknown disappears, this one here. So now you actually have only 1, 2 unknown, and therefore you can also calculate the weight of this to keep it in equilibrium, the weight of this container at E. So rather than solving this problem for you, because you already did this anyways, but I'm going to show you that first I would do the free body diagram for node B. Then second, I would find equilibrium, so equilibrium equations. for node B. And that would really give me, if I solve this, so solve, this would give me FAB and FBC. So that in my third step, I can now apply force FBC to node C. And please understand that FBC is a tensile force, right? Is tensile force. And therefore must pull away from node C. So this can often be confusing because students think, hey, I calculated my force for node B and BC was pulling to the left. It's away from the node, therefore in tension. So if it's going to the left here, then up here in node C, it has to go to the left as well, is what they think. But that is incorrect because remember that we're talking about tension and we cut the system. So if I draw that in here, you will see that here I have tension because I cut there. And of course, tension cannot change to compression just because you move to a different node. So up here at node C, there must also be tension. And now you may ask yourself, how is that possible? There are two arrows pointing towards each other. But keep in mind that you actually did a cut here and you did a cut here. And therefore, you actually have this middle part also in tension. And that really allows you to keep equilibrium throughout, and also makes sure that you have tension from here to here, from here to here, and from here to here. So please understand that you need to apply the force sometimes opposite depending on what force state you are dealing with here. But yeah, so my point to you is pull away from node C. So once you did that, you can now apply this force. And so in my fourth step, I can now draw the free body diagram. So fourth, which is free body diagram for node C. And then fifth step is to use equilibrium to solve for node C. And once you have that, you can really answer the entire problem where it says find all the cable forces in the system. And so I probably don't need to solve this for you here numerically. In fact, it is a good practice for you to do that yourself. But so you can check your answer, let me just tell you that if you solve this properly and you find the ultimate answer, which is the weight of the container at E, you will find that weight of container E is equal to 0.975 pounds. 0.975 pounds. And that is an answer here, so I guess I got to double underline it. And that is the answer you should arrive at if you solve this properly. And I really encourage you to do this and find a way to check your results. One way, for example, of checking your results is, let's write down the overall equation for this cut cloud. So let's say that you make this cut. For example, this is one way to look at it, which is effectively the entire system. So if you apply the 4 pounds down here, and then the 0.975, then you should find that the sum of your forces that are released here, which is going up, and here, which is going up, that those two forces, and maybe I should give them a different color. Let me do that. Let me make them orange here for you. So this plus this, of course, needs to be 4.975 pounds. That is the force that needs to pull up. So please double check your answer here and make sure that your force is pulling up with 4.97 pounds. This plus this must be equal to this. That is once again the sum of the forces in the x direction. But now you have all the tools that you need to solve this problem. I wish you good luck with that. And let's move on to our homework.